Let's get into anaerobic digestion. This is chapter 12, I believe, in the OTCO Basic Wastewater course, anaerobic digestion. So, anaerobic digestion. What we're doing here is trying to take that sludge material that we talked about in the previous chapter. And of course, we talked about trying to concentrate that sludge, remove some of the water to make it more cost effective to dispose of. With anaerobic digestion, we're just taking that concept a little bit further. So the purpose of anaerobic digestion really is to process the sludge and treat it to the extent that we can either apply it to local farm fields or treat it to the extent that it's safe for use as a fertilizer or a soil amendment by the general public. So this is called beneficial reuse. And when we beneficially reuse the sewage sludge, it goes from being sludge to being something called biosolids. But the ultimate goal for us at the wastewater plant, by being able to land apply it or give it away to the general public, is that makes it less costly for us to dispose of. Of course, there is some benefit to reusing it. We're able to recycle phosphorus and nitrogen in that sewage sludge back into the soil. So it is environmentally helpful, especially in an area like Ohio that relies heavily on farming. But our main purpose for beneficial reuse of the wastewater plant is that it's much less expensive for us to dispose of. In our case at Perrysburg, it is about 3 times more expensive to haul this sludge to a sanitary landfill than it is to land apply it on local farm fields. So when we talk about biosolids, we're talking about Class A or Class B biosolids. Those are the 2 categories that can be land applied. Class A, as I mentioned, has been treated to the extent that it's safe for use by the general public. They can come and pick it up and use it in their gardens or in their landscaping at home. Class B biosolids have been treated to the extent that they're safe for land application on agricultural fields. Now, there are some rules about that we'll get into down the road. But for right now, all you need to know is that the difference between Class A and Class B biosolids are that Class A biosolids are going to have stricter requirements for pathogen reduction, and Class B biosolids are going to have pathogen reduction and vector attraction requirements. And those can be met by a variety of ways. At the Perrysburg plant, we meet pathogen reduction requirements by holding our sludge for a certain amount of time and at a certain temperature. In our case, 95 degrees Fahrenheit for 15 days. When we talk about vector attraction, we're talking about stabilizing the sludge so that it does not attract nuisance organisms like flies. And we are able to meet that requirement at Perrysburg by showing a % volatile reduction. The sludge that goes in to our anaerobic digesters, maybe 75 to 80% volatile content. The sludge that comes out of the digesters has been reduced to anywhere between 55 and 60% volatile content. That % volatile reduction, which you will see in your math homework and which there is a specific formula, at least in our case, has to be greater than 38% in order for our sludge to meet Class B requirements. From there, if your sludge meets the Class B biosolids requirements, and there are a few other requirements just besides pathogen reduction and vector attraction reduction. There are limits on metals, things like that, but if your sludge meets those Class B requirements, then it can be land applied. And as I mentioned, generally land application is far less expensive than hauling it to a landfill. Okay, so let's talk a little bit more about the anaerobic digestion, say, versus aerobic digestion. What are the advantages and disadvantages of anaerobic digestion? Well, the main advantage is that anaerobic digestion produces a desirable byproduct, methane gas, which some plants use to create energy. We use it at the Perrysburg plant to heat our anaerobic digesters. Other plants may use it to generate electricity. Uh, Along with the methane gas production, with the methane being a desirable byproduct, as I've mentioned, with the heating and with the electricity, it has lower energy requirements than aerobic digestion, simply because number one, you can generate some of that energy on site through the methane gas, and secondly, aerobic digestion requires an awful lot of electricity to power the blowers needed to generate enough oxygen for your aerobic digesters. Another advantage of anaerobic digestion is relatively odorless. Anaerobic digesters are more or less sealed from the atmosphere, so very little odor associated with it while the process is going on. Disadvantages of anaerobic digestion, I would say that the operation of an anaerobic digester is more complex than an aerobic digester and requires probably closer attention on the part of the operators. And also those byproducts that we've talked about, the methane gas and a little bit of hydrogen sulfide, those gases are explosive when mixed with air in the right concentration. So the byproducts, while desirable, are also dangerous. And finally, I would say trying to maintain anaerobic digesters can be difficult. A lot of confined space entries, a lot of work inside enclosed vessels with potentially hazardous atmospheres. Those would be the disadvantages of anaerobic digestion. Okay, so let's talk a little bit about the operation of anaerobic digesters. Uh, First thing you need to know is that anaerobic digestion is a two-stage process, two different types of bacteria. Acid-forming bacteria, which convert organic material into volatile acids, and then methane-forming bacteria that convert those volatile acids into methane gas. The acid-forming bacteria work pretty quickly. The methane-forming bacteria do not. So it's important not to let the acid-forming bacteria work so quickly that the methane-forming bacteria cannot keep up. If the acid formers outperform the methane formers, you can run into a situation where all of those volatile acids will soak up the alkalinity in the digester and eventually halt the process, and you get what's called a sour or stuck digester. So An important lab test to do in process control for anaerobic digesters would be your volatile acid and alkalinity testing. And then there's a volatile acid to alkalinity ratio that you need to maintain so that you do not get too many volatile acids disrupting the anaerobic digestion process. So you'll probably see some of those math questions in your homework. Actually, two separate tests, one for volatile acids and then a second for alkalinity. And then you take those results and calculate a ratio that has to be within a certain range. Eventually, the pH in the digester will start to drop if you're getting too many volatile acids being formed in the digester. But usually by the time that you see significant changes in the pH, it's too late for that digester to recover without some intervention on your part. So two types of bacteria. Acid forming bacteria, remember, work very quickly. Methane forming bacteria work more slowly. The methane formers are much more sensitive to changes in the environment. So it's highly recommended that you not change feed rates to the digesters by more than, say, 5 to 10% per day. And also, this is very important. You will definitely see this on an exam. Do not change the digester temperature by more than 1 degree Fahrenheit per day. As far as the digesters themselves, there are 3 different temperature ranges where anaerobic digestion can take place: cryophilic, mesophilic, and thermophilic. So I always remember these by cryo being cold, like cryogenic. I guess I always think about Han Solo in the Empire Strikes Back being frozen cryogenically. Cryo means cold, colder temperatures. Mesophilic, meso, kind of in the middle of the temperature range. We're probably talking like anywhere from 83 to about 113 degrees. This is the range that most wastewater treatment plant anaerobic digesters are going to operate in. And for the most part, we're looking to maintain temperature right around 95 degrees Fahrenheit. Thermophilic, thermo would be the hottest. I think the range of thermophilic digestion takes place anywhere above 113 degrees. This is a more efficient digestive process, but generally not widely used because the energy requirements to heat the digesters to that temperature range are just too great. So most anaerobic digestion at wastewater plants is going to occur in the mesophilic range. As I mentioned in the previous slide, our pathogen reduction requirements require 95 degrees and a detention time in the primary digesters of 15 days. So also, if possible, it's good to mix the contents of the digesters so that incoming raw sludge or thickened sludge, the sludge being put into the digester to be digested is mixed throughout the contents of the digester, and you get more of a homogeneous sludge inside the digester. Allows for more efficient digestion. So mixing is highly recommended. Heating the sludge as it goes into the digester is recommended. So typically at a plant with the anaerobic digestion, when you're pumping that colder sludge from the treatment plant into the digester, a lot of times that piping is going to route the sludge through the heat exchangers before it even gets into the digester to try to help heat it up a little bit and mix it with some of the heated sludge in the digester. A little bit more about operating anaerobic digesters. Let's talk a little bit about covers. The digesters here at the Perrysburg plant have floating covers. These are covers that float on top of the sludge. There are supports inside the digester for the cover to rest on when the liquid level drops below a certain point. Floating covers can occasionally get stuck. So that's a concern with the floating cover digester. Floating cover digesters also have been known to sink at times. The floating cover has a space between what I would call the roof of that digester lid and let's say the ceiling or the internal like bottom part that you would see if you were actually inside the digester. There's a space in between called the annular space that's filled with air that allows that cover to float up and down on the sludge. If the roof of your digester lid should happen to leak and rainwater is allowed to build up in that annular space, it can reduce the buoyancy of your digester lid to the extent that it actually will sink into the sludge. Fixed cover digesters, just like it states, fixed covers are kind of permanent. They do not move up and down. One of the risks of having a fixed cover digester is they can be susceptible to pressure or vacuum. Removing sludge too quickly from a fixed cover digester has in the past caused fixed cover digester roofs to collapse because of the vacuum. So that's something to be careful of with fixed cover digesters, not filling them or removing sludge too quickly. Either one can create issues. The last type of digester cover with anaerobic digesters are like a gas storing a digester cover. These kind of resemble balloons, and they'll inflate and deflate as gas pressure builds and allow storage of methane gas in the digester, generally for use in creating energy. Another operational consideration of anaerobic digesters to be aware of is condensation. These digesters are producing methane gas, so you have a relatively warm, remember we're trying to heat these around 95 to 96 degrees. So you have a warm, relatively moist or humid gas traveling through piping that when it goes outside the digester is surrounded by air that's much colder. So you'll get a fair amount of condensation. That condensation it has to be removed sometimes several times a day in the wintertime. So gas piping in anaerobic digesters as it leaves the digester is designed to have these condensation traps at low points in the piping where condensation will be collected, and those have to be emptied on a regular basis. Scum and grit in an anaerobic digester can create issues. They can accumulate and reduce the usable space. I've seen some textbooks and reference material recommend that anaerobic digesters be cleaned out, say at least once every 5 years. I know at our plant in Perrysburg, we've cleaned several of them in the past few years and seen quite a bit of buildup of grit. All that gritty material that comes into the wastewater plant and gets pumped into the digesters with sludge settles to the bottom, and it just will collect there and build up and actually reduce the available volume for digestion. So that's something to be aware of. And the last thing that I'll touch on to close this out is supernatant. This is a clear layer of water that can be withdrawn from digesters if the solid material is allowed to settle. At our plant in Perrysburg, we have two primary digesters that are heated and mixed, where all of the digestion actually takes place. Those are the digesters where we have to meet that 15 days and 95-degree target. And then we have two other digesters that are storage digesters. And we will pump sludge from the primary digesters to these secondary digesters. And if that sludge is allowed to sit there for a few days, the solid material sinks to the bottom, and sometimes there will be a relatively clear layer of water on top, and we can draw that water off the top and send it back through the plant for treatment, which is, of course, cheaper than running it across our belt filter presses. A couple things to be aware of, though, with supernatant. It's very high in ammonia and phosphorus, so you have to be careful about the additional loading that it puts on your plant. And in our case, when we withdraw a high amount of supernatant and it gets fed back through the plant, we can actually see the dissolved oxygen in our aeration tanks just drop like a rock when that flow goes from the primary settling tank into aeration. We see the same effect when we run the belt filter presses with the belt press filtrate, that sort of thing. So if you're at a plant that's staffed 24 hours a day, probably going to be pretty common practice to withdraw supernatant from your digesters on third shift or in the middle of the night when loading on the plant is low. In our case, we're only staffed from 7 to 3:30 during the day, so we're looking at making accommodation where we can withdraw supernatant from the digesters, but then store it and pump it back through the plant on a timer later in the evening. So be aware, pretty heavy ammonia and phosphorus loading in that supernatant. As I mentioned, it certainly is a lot cheaper to withdraw that clear water off the top and run it back through the plant than running all of that sludge across your belt filter press to dewater it. But to be aware that it can put a pretty serious load on the plant. So there you go, a little bit more about anaerobic digestion, and that's all I got.